So we'll be in MH 480 starting next week. I will still plan to record these lectures though. I know some people like to look back at them and review them from time to time, so I will do that. And I will also continue to have my office hours in Zoom as well as in person. So starting next week, you'll be able to pick your choice if you want to stop by my office or if you want to come in person. Either way, we'll be fine starting next week. Um, let's see. Also, just so everybody's aware, next Tuesday is kind of an important day for enrollment. It's the last day that you can drop this class without getting a W on your transcript. So if you want it to look like this never happened, you would need to get out of here by next Tuesday, withdrawing from the class. Otherwise, you'll get a W if you withdraw later than Tuesday. Also, next Tuesday is also the last day to add this class without getting a whole bunch of extra signatures and permissions and paying a fee and all of that. So I will be back obviously next week. And so if there's any last minute enrollment issues, I'll be right there on the ground. I can try to work on things then. But of course, for the most part, I can do things electronically as well. So if you're having an issue one way or the other, either trying to enroll or trying to get out, and you need some help, let me know and I'll do my best with that. Also, there is a homework assignment due tomorrow night. Just to remind you, I did update the due date to be tomorrow night in Canvas, and I have office hours. I haven't been very busy this week. I was pretty busy last week. This week has been pretty quiet so far, but I do have office hours tonight after my other classes. I have my 250B classes until 8 o'clock. So at 8 o'clock, I'll be in Zoom. This week is still Zoom only. So tonight at 8 o'clock in Zoom, or tomorrow night from 7 to 10 p.m. in Zoom. So if you need help, just want some hints, or just want me to talk over anything from the homework with you, or anything from the lecture as well, I'm always happy to do that. So feel free to drop in either tonight or tomorrow night in Zoom for that. Also, I just got some good news today. It turns out that one of our math majors, who is very advanced, and he's going to be graduating, I think, this coming spring. He is really, really good. He's like a once in a decade kind of student in our department in terms of just, he loves pure math. He eats and breathes it. Turns out he's been assigned to have office hours for us in this class, and he's going to start next week. His name is Jaden Segovia, and some of you may know him. He's pretty much run the whole gamut of our math major courses by now, but he is going to be able to have a couple of office hours. I think actually more than a couple. I think he's going to have office hours every day, Monday through Thursday. I forget the exact times. This weekend, I'm going to, as always, send out my weekly sort of overview of what's going on. And in that email, I will tell you more about Jaden, when you can find him, where you can find him. But pretty much every day, Monday through Thursday, I think he's going to have some office hours, which is really, really good. He explains stuff really, really well, but at the same time, he's also really down to earth with everything. And I think he can relate well to pretty much any level. So I was really stoked to hear that the math department is going to pay him to help us. So we have an extra resource for this class. Let me see, was there anything else that I needed to mention for now? I don't think so. As I said, I will be traveling back over the weekend. The plan is by Monday night, I should have my office hours on Monday night again. And there is homework due on Tuesday. So by Monday night, I should be back in Fullerton. So you'll be able to come to Zoom as usual to talk with me. But you could also come down to campus if you wanted to on Monday evening, and I should be there, assuming everything goes according to plan this weekend with my travels. So anyway, that's kind of where we are at. And there's some loud noises going on outside here. So I'm getting distracted a little bit. Does anybody have any questions as we get started today, guys? So far, so good. Oh, I do have my chat box open like always. So if you do think of any question, feel free to throw it into the chat and we can talk about it. But yeah, for sure. Feel free to drop by if you've got questions on the homework that's due tomorrow night. I am eager to help, and I'll always do my best to give you some hints and give you some pointers on it. I think there's some good problems, the ones for tomorrow night. So I think that'll be good. It's still review problems, just dealing with functions, images and pre-images and surjections, injections, bijections, all that material that we've kind of been talking about up until now. It should be a good review for you. Now, some of the material that we did on Tuesday, which I've kind of reminded you about here on my whiteboard, actually probably isn't a review for most of you, this concept of a countable set. And so I want to just recap this here, and then we're going to press on with some more material today. And again, I'm probably going to be talking for most of the 2 hours about this material. I promise once I'm back next week in person, we'll take breaks, we'll do group work, we'll get a little more interactive with things. But for today, I'll probably try to see how far I can push through on some of this material, if that's all right. Okay, so anyway, I defined a countable set on Tuesday. This is just a set that by definition is either finite or there is a bijection with the natural numbers. Okay, so one way or the other. If A has a bijection with the natural numbers, that just means that A is countably infinite. Okay, so there's this extra word in here. Countably infinite just means that A is in bijection with the natural numbers. There exists a bijection between the set A and the natural numbers. Okay? Otherwise, if A is not finite and if it is not in bijection with the natural numbers, then it's uncountable, right? So these are the basic terminologies here. And this remark that I've kind of put here on the board, I talked about it on Tuesday, but I just wanted to kind of like get it printed out in black and white for you here. This just says that if there is a bijection, so if A is countably infinite, and therefore there is a bijection from the natural numbers to your set A, then in that case, the entire set A can be listed. It can be listed as the images of the function, f of 1, f of 2, f of 3, f of 4, right? You can list out all of the outputs of the function, and the fact that f is onto means that everything in A must be f of something. So you'll eventually find all of the elements of A listed out in this set, right? And we sort of have an ordering here, right? There's the first element is f of 1, the second element is f of 2, the third element is f of 3, and so on. If you gave me any element of A, I could find it in this list as f of something, right? So this is kind of the power of having a bijection between these sets, okay? So that's another way to think about a countably infinite set, is that even though it's infinite, we can still methodically list out all of the elements in a way that will cover every element, right? Nothing will ever be missing from that, okay? So this is just kind of getting the terminology back in mind. Is everybody good with this? Are there any questions here before I maybe tackle something slightly new? Okay, great. So if we're doing good so far, I just always like to start with a little recap. I'll be doing that next week too when we get back in person. I would like to summarize what did we do in the last class, or at least some of the highlights of it. And so this is a good sort of starting point for us to begin with today. Well, I am going to state a proposition right here. And again, I will use numbers from the book. And you guys don't need to memorize these numbers for any reason. I'll try my best to put them in my lecture notes, though, so that you can line things up with the book as appropriate. This is a proposition that has 4 parts to it, and it might start to look familiar to you as I start writing it down. So there's going to be 4 parts here. I think I can write the whole thing down in this space I have here on the left side of my board. So let's just see if I can do that. So what this says, part 1, is just saying that if A is countable, so if A is countable and A is in bijection with B, so if A twiddles B, again, that just means there exists a bijection between the sets, right? So if that's the case, then B is countable. Okay, so if one set is countable and you can make a bijection from that set to another set, well, then the other set is also countable. And then the second part of this proposition is going to do the same thing for uncountable. All right, so I'll write it out this way. If B is uncountable, and again, I'm going to assume that A is in bijection with B, so A twiddles B. Then A is uncountable, right? So it really just means that the issue of whether a set is countable or not must be preserved by a bijection. So if two sets are in bijection with each other, then they're both going to be countable or they're both going to be uncountable, right? That's pretty much what that's saying. Okay, and then the third part here, I'll just keep going. If A is countable, and we take B as a subset of A, right, then B is also countable. So if you start with a countable set, remember, I like to intuitively think of a countable set as being kind of a small size of an infinite set. It's like a small version of infinity. So anything inside of a countable set is even smaller, right? So if the original set was countable to begin with, then anything inside of it will also be countable. Again, I prefer to just have an intuitive sort of appreciation of this more than just having this memorized, right? It should just kind of make sense. Countable is kind of small, right? The set could be infinite in size, but it's sort of a small flavor of infinity. So it's fairly small, and therefore anything inside of it is also still very small. So if A is countable, any subset of A is still going to be countable. Right, and then the last statement, of course, is going to just be the flipped over version of that, which would just be if B is uncountable and B is a subset of A. Okay, so now uncountable is kind of the big size of infinity. So if B is already kind of a big infinite set, then if A is a superset of B, then A is even bigger, right? So as I'm sure you will appreciate, the conclusion is going to be that A is also uncountable. That's the conclusion here. All right, so hopefully pretty much makes sense. Okay. Does this proposition remind you of anything? From Tuesday's class, I guess, to be specific. I didn't put it in my recap, and maybe I should have. But if you right, Ayushi's kind of got it in the chat for us here. There was a proposition. It was actually 2.8 that we did on Tuesday, which had 4 parts, and it was dealing with finite versus infinite sets, and it was actually pretty much the same 4 statements. I'm just going to make that as a remark so that when you're kind of trying to study all of this stuff, you can make that connection. It'll maybe save you a little bit of time. These 4 statements align to proposition 2.8, prop 2.8, with, and then I'll just make the correspondence here, countable is kind of lining up with finite, and then uncountable kind of lines up with infinite. So if you can make that association, if you can connect countable with finite and uncountable with infinite, then actually you could take proposition 2.8 and just change every place that you see the word finite to countable, and take everywhere you see the word infinite and change it to uncountable, and you're going to have this proposition. So I know it feels like a lot of material here, but this one is almost just a mirror image, a reflection in the mirror of that earlier proposition. So in that sense, it's not so bad. I decided, because it is 4 parts and it's kind of similar to that earlier proposition, I actually reviewed my proof of this proposition again recently, and I said, you know what, this is very much in the same spirit, the same flavor as the proposition 2.8. So what I'm going to do, instead of taking class time to write out another 4 proofs right now, I am going to make a video. I have not done it yet, so it might take me a little bit of time, but I'm going to make a video for that and just have you watch that on your own time. Alternatively, before I get the video done, if any of you, once you get done with tomorrow's homework assignment, you just want to practice this a little bit harder, you could try to do the proof by taking the earlier proposition and literally, just as best as possible, try to just tweak it or mimic what was done in that earlier proof that we did do on Tuesday, and see if you could try to write out this proof. That would actually be a good exercise. But I will make a video anyway, just so that you guys can look at that later. But I think I'll save the time from doing that for right now. I don't think I need to do it right now. Is everybody okay? Are there any questions on this? Let me know if you can't see anything as well. I mean, I'm trying to put my cameras as close to the board as possible so that it's all readable. But at the same time, I don't want to cut anything off. So if I'm missing anything here, be sure to let me know. Okay, well, on Tuesday, we also had a proposition 2.9, which was kind of a follow-up to proposition 2.8, and we used 2.8 to prove 2.9. Guess what? There is a natural follow-up to this proposition as well that we can state right now as well, and it also follows very naturally from the proposition that we just wrote down. So this is 2.12, and this one has 2 parts. The first part, again, guys, we're just going to take 2.9 that we did on Tuesday, and we are simply going to take the word finite and change it to countable, and we're going to take the word infinite and change it to uncountable. That's all that's going to happen right now. So let me just state the first part. If A is countable. So if A is countable and there exists a function f that goes, let's say, from A to B, and this is onto. So I'm going to write the word onto right here, just like I did on Tuesday for the earlier proposition. So if your domain is countable and you make a function that is onto another set B, which is the codomain, then B is countable. All right, so that's nice to know. And again, in proposition 2.9 that we had on Tuesday, the word countable just appeared as the word finite. And that was it. Everything else about it was exactly the same statement. So no big shocker there. And then the second statement here, I'll write this one down as well, guys. This one is just saying if A is uncountable, right? And there exists an F, which is going from A 1 to 1 into B. So here I'm using that little fish hook arrow again. I did this on Tuesday as well to kind of suggest that this is a 1-to-1 function. It's just kind of a notation. It's not absolutely required. But if your domain is uncountable and you create an injection to another set B in the codomain, then B is uncountable. Okay, so uncountable is sort of preserved by injections, in other words. I think I'll go ahead and do the proof of this proposition because it only has two parts and they are pretty quick. And also it's kind of a good chance to practice some of the reasoning that we're going to be using in the results that we're going to do later today. So I think this would be a pretty good time to do this one. I'll go ahead and do this one right now in the lecture. I am going to be assuming the earlier proposition though, which I didn't prove yet, but that's okay. We'll trust that it's going to be true. This has never happened before, right? That there was some unproven conjecture that got used to prove a bunch of other things. Actually, I think some mathematicians might have some interesting stories about that to share with you. Anyway, I will not bore you with that for right now. But let's prove the first part here. If A is countable and we have an onto function, then B is countable. Okay. The way I'm going to do this is I'm going to use the onto property immediately. And the way I can do that is I can just say for each little b in capital B, right? Since F is onto, so for each element of the codomain, since the function is onto, there has to exist some A sub B in capital A with F of A sub B equal to B. Right, so that's something that you saw on Tuesday. We did this kind of idea. So we take this element in the codomain and we pull it back with a preimage. Now there might be multiple preimages. Okay, this is not necessarily a one-to-one function, but we don't care if there are multiple preimages. We just need to pick one, right? We may pick a preimage here as such. Okay, and so this allows us to create a function g. So we define, again, you've pretty much seen this proof already, just with the words finite instead of countable, but that's okay. I'm going to define a function g that goes from B to A via g of B equals A sub B, like so. Right? And then I'm just going to, so you just take the element of B and you map it to whichever preimage you chose. And two different elements B cannot be mapped to the same point because that would mean that, you know, your preimage of, if your preimage of B and your preimage of C were the same, then that element in the set A would be mapping out to two different points, which isn't a function. So this is one-to-one. So I would just note G is one-to-one. On Tuesday, I wrote that all the way out. I wrote out the full proof. Okay, if G of B equals G of C, then B equals C. Okay, I won't write that all out again today. I'm just going to leave it as this because it is the exact same thing that you've already got in your notes one time. But let's see what we can do with that. So thus, B twiddles G of B. All right, so this is that trick. Do you remember the trick from Tuesday? The trick was that if you have a one-to-one function, which we do right now, if we have a one-to-one function, then you can view it as a bijection from B to whatever the range of the function is. And the range of the function is just G of capital B. It's the image of the entire domain. So G itself might not be onto, but the G would be onto if the codomain was just restricted down to whatever G of B is. And then you would end up with a perfect bijection. And G of B is sitting inside of A. It's a subset of A, right? Well, let's take a look at our proposition over here. What do we know? We have that A is countable, and G of B is a subset of A. This is part 3 over here. If we have a countable set and then we look at a subset of it, then that subset is countable. So G of B is countable. And then what does part 1 say? Part 1 says that if one set is countable and it twiddles another set, then the other set is also countable. So you see, putting those two things together, if A is countable, then so is G of B, and therefore so is B. Okay, so I'm just going to say here, just come over here so I don't block the board too badly. By proposition 2.11, I'm using 1 and 3. So I'm using parts 1 and 3 right now. B is countable. So a subset of a countable set is countable, and then if two sets are in bijection and one of them is countable, so is the other. So that's what we wanted to prove. So the image of a countable set, I'm just going to say this really, really succinctly. The image of a countable set is always countable. That's really what statement 1 of this proposition is saying. The image of a countable set is always countable. Okay, fantastic. Any questions so far, guys, about this proof? That's the first part of it. Okay, let's talk about the second part of this proof then, if everybody's good. And I do have my chat box open, guys, and I'm more than welcome to, you're more than welcome to turn on your microphone. You want to ask me a question, I will try my best to answer it, okay? Let's look at part 2 of this proposition. So I'm talking about this part 2 right here. I'm now going to prove it. If A is uncountable and we have an injection into B, a one-to-one function, in other words, into B, then B is uncountable. So guys, this is just a one-liner. This is just a one-liner because we can just write this very quick. Well, it might not be one line on this board. This board's a little small, but it could be done in a basically one sentence. A obviously is in bijection with F of A. I'm using that same idea again. It's one-to-one already. F is already one-to-one on part 2. And so therefore it is a bijection onto its image, right? So that trick is just coming up many, many times. And then F of A is sitting as a subset of B again. We have all of that like before. And what is my assumption here? My assumption is that A is uncountable. Okay, so let's kind of look at parts 2 and 4 of this earlier proposition. If one set is uncountable and it twiddles another one, then the other set is also uncountable, right? So up there, A is uncountable. That's the assumption on number 2. So therefore, F of A is uncountable. And then B, we do have to switch the roles of the B around. The B is actually going to be the superset in this proof right now. But if you take a set that's uncountable and then you build a larger set around it, that larger set is still uncountable. So I'm just going to wrap this up. B is uncountable by proposition 2.11, and this time I'm talking about parts 2 and 4. Parts 2 and 4. So that's a very short proof. We don't have to work any harder than that. Questions here, guys? Okay, let me give myself a little room over here. Now we're going to kind of switch gears. Well, not really switch gears. We're going to keep talking about countable sets, but there is a really big theorem that we're coming to today. This is one that we will definitely be coming back to. Before I state it, I need to prove one other little lemma first. Of course, the natural numbers, this is just a lemma. Lemma is just a result that helps us prove another result. So I'm just going to state this lemma, which is taking the natural numbers. Now, we already know that the natural numbers are countable. They're countably infinite, in fact. But if we cross the natural numbers with themselves, right, then this is even countable. This is still countable. So the natural numbers cross the natural numbers is actually countable. And remember, this is Cartesian product, right? This is ordered pairs is what the natural numbers crossed with themselves is. And so how am I going to prove this? This is a nice little proof as well, guys. I like this one because it uses a little bit of number theory. And I'm an algebraist at my core. I love number theory. So we're going to do just a little bit of number theory here. We're going to define a function f going from n cross n over to n via, so I'm going to make a function. I'm creating a function right now to try to prove that n cross n is countable. And the way I'm going to make my function, guys, is I'm going to take f of n, f of, let's just use a and b here. F of a comma b, and the natural number that I'm going to spit out is 2 to the power of a times 3 to the power of b. All right. So there is your function. And I'm going to start by claiming here that f is actually 1-to-1. I claim that this is actually 1-to-1. And that's where the number theory comes in, which is really cool. If we assume that f of a comma b is equal to f of c comma d, so we take, this is how we prove 1-to-1, right? Assume that f of one input is equal to f of another input. So it might look something like that, f of a comma b equals f of c comma d. Then I'm going to try to prove for you guys that ab is equal to cd, right? Now, from the assumption, of course, what we're saying is that 2 to the a, 3 to the b is equal to 2 to the c, 3 to the d. Okay? And let me start by looking at the powers of 2 on both sides of this equation. Without loss of generality, we can assume that the A is greater than or equal to C. I mean, one of them has to be greater than or equal to the other. So just without loss of generality, I'm just going to assume that we have set this up in a situation where the A is greater than or equal to C. But if A is actually greater than C, if it's strictly greater than C, then, so if the exponents on the 2 are not the same, I can start canceling the 2's from both sides of the equation, right? I can cancel the 2's, and what will the math look like after I do that? I'll have 2 to the a minus c, 3 to the b equals 3 to the d. So you'd have something like that. And in this case, well, I think you see the contradiction, right? The right-hand side is definitely an odd number. 3 to whatever power, it's definitely odd. On the left side, if a is bigger than c, then this exponent is at least 1. And that means the left-hand side is an even number. You have an even number equal to an odd number, right? So this is even. It's just a little bit of number theory, which I kind of like, seeing this in the middle of what we're doing here. Even and odd, and so that is a contradiction. Looks like I might need just a tad bit more room here. Don't forget this proposition, guys. I'm going to erase it right now. Actually, I don't need to erase it. I'm going to use the space over here. I want to keep that proposition up for a minute because we're going to use it to do this lemma. So let me just move over. I'll save the bottom part of my board and just come up here for the time being. But this is a contradiction. Okay, so if it's a contradiction, what do we conclude right now? Why don't you, do you guys all have your chat box handy there? I just want to see if anybody's alive out there. Could you take your chat box and just type in, what would you conclude now based on having reached this composition? Just send it to everyone, and then let's just see if anybody agrees with what we're supposed to say next here. Nice thing about Zoom, I can just have people throw stuff into a chat. I should have about 18 answers coming in. So far, I've got a couple answers. Again, without loss of generality, we have said that A is greater than or equal to C, but then I'm assuming here that A is strictly greater than C. But what conclusion would we have from that? Okay, now I'm starting to get some folks responding exactly right. So we're definitely going to conclude that A is equal to C, right? So this is a contradiction, and thus the conclusion of that is that A is therefore equal to C. Right, so that's what we have. Well, let's go back. If A is equal to C right here, guys, here's my starting point. If A is equal to C, then I can cancel all of the 2's from both sides. So canceling above, we get, well, it's going to be 3 to the B equals 3 to the D. The powers of 2 are going to be canceling because there's the same number of them on both sides. All right, and if 3 to the B is equal to 3 to the D, then I'm pretty confident that that implies then that B is equal to D. Okay, and so hence A comma B is equal to C comma D, and that's good. That's proving that my function here is one-to-one. Okay, do you think you can finish the proof now? In my notes, it's only about a line that we have to write down. We have a one-to-one function f. Let's take a look right here. F right here, this is one-to-one now, right? And I'm trying to prove that n cross n is countable, right? There's actually sort of 2 ways that we could do that. Usually, actually, this function is not surjective. It's definitely not surjective. You notice the outputs are never going to have factors of 5 in them or factors of 7. It's not surjective, but the good news is that these propositions over here, right, they didn't require us to have a bijection. We only needed to have either an onto or a one-to-one function. At this moment, we have a one-to-one function, which is what part 2 is about, right? Hyunjun, you're absolutely right. Hyunjun's making a good point, which is essentially how part 2 of this proposition was proven, which is that, again, what's my big trick that we've been using all these last couple of days? If you have a one-to-one function, which we do, right, then you can make a bijection from the domain to whatever the image is. So thus, n cross n is in bijection with its image. Okay, so this is since f is one-to-one. So we have now seen this argument going on half a dozen times already, right? So since the function f is one-to-one, then there's a bijection from n cross n to its image. And its image might not be the whole natural numbers. It's not necessarily onto, but it's definitely inside of n. And remember, guys, n is already countable because it's in bijection with itself. Remember, countable just means A twiddles n. So in this case, n twiddles n. So that's countable, and we're looking at basically the same proof that we were doing 5 minutes ago down here in part 2 of this well, actually, part 2 of the proposition I proved, I erased it, but it's basically this same argument. So let me just finish it up here. We'll write down just one more little thing, and then I think we're going to be done. So thus, n cross n is countable by, I'm just going to go ahead and use proposition 2.11 parts 1 and 3 again. Yeah, we can just do that. We have a set that's countable. So here's a subset of a countable set. That means that's countable. And if it's countable and it twiddles something else, then that other thing is also countable. Guys, you can also do this by way of contradiction. If you want to use the proposition 2.12, you could say, well, by contradiction, suppose n cross n is uncountable. And then you have basically you have a superset of an uncountable set. And you can also do it that way. It's totally equivalent. Okay. But this is certainly a reasonable way to do it. Okay. So n cross n is countable. Basically, guys, what we're heading towards, just to give you the big picture view of this for a moment, what we're heading towards is we're going to prove that a lot of sets are countable. But I don't want to have to do that by constantly creating bijections with the natural numbers. I want to have some theorems, some powerful results that allow us to deduce that things are countable very quickly. Okay, and I'm ready now to state what is really the ultimate result. The ultimate theorem that comes from this lemma that is incredibly useful for proving that tons and tons of sets are actually countable. And remember, guys, countable is important. It means we can list out all of the elements of that set. Okay, so this is a theorem that you will want to put into neon lights. It is the most important theorem in this chapter. And so I'm going to want to prove this one really carefully. So I saw somebody just sent me something in the chat, but I don't see it. So maybe it needs to go, make sure that you're sending your notes to everyone. Otherwise, I'm not going to maybe see it. Okay, so here's the theorem, 2.4. A countable union of countable sets is countable. A countable union of countable sets is countable. It rolls off the tongue really nicely. It's actually relatively easy to kind of memorize this result because it reads really, really easily. So if I have some sets that are already countable, and I take their union, of course, when you take the union, you make the set bigger, so you run a risk that maybe it could become uncountable. But no. As long as you only took countably many sets that were all countable in the first place, then that union is still countable. So that's what this means. Okay, so it's good to pause and make sure you understand what we're saying here. The number of sets that we have is countable, and each one of them is individually countable. If we take the union in that kind of a situation, the result is still countable. So maybe I should, this is the way you would read it out. A mathematician would talk casually in a coffee break. They'd probably say it this way. But how would it look if we wanted to sort of write it out more nicely? I'm just going to explain it here, i.e., how could we write this theorem in a way that would be more mathematically appropriate? Well, if capital I is a countable index set, right? And for each, if capital I is a countable index set, and for each alpha in capital I, the set A sub alpha is countable. So you have a whole family of countable sets here. These are these A sub alphas, okay? Then if you do the union of all of those, so I'm doing this, remember we talked about this last week, this idea of doing an arbitrary union of sets? If I take the union of all of those A sub alphas, this is still countable. So this is a more mathy way. It's kind of a more mathematical way of actually writing the statement. Okay, so using some notation and so on. Okay, so I'm going to give you a minute to kind of chew on that and recall the arbitrary union notation there. And then we're going to prove this result. I think I can finally get rid of this proposition now. We've kind of done as much with that as we need for the time being. It's just a little hard to erase this board. That is my only gripe about this setup. I finally got the lighting to work well in here though. I used to have problems not just with erasing, but also with lighting. Now it's mostly just the erasing that I don't like to do. Okay, great. So with that in mind, are there any questions here about this statement? Feel free to throw them in the chat or use your microphone. I'm going to prove the statement, and then the fun part is the applications of it, because this is an extremely applicable result. So let's do the proof here first. Come back over here. Another proof. When you signed up for this class, I assume you were expecting to see lots of proofs. That's what this class is mostly about, and you're certainly getting a taste of that here. Hyungjun is asking, is there an example of an uncountable union of sets? Well, first of all, an example of an uncountable set would need to be in our minds, and I would probably think about the real numbers. Okay, so if your index set, if capital I was the whole real numbers, that would be an uncountable union that you would be forming in that case. And so in that case, this theorem would not apply. This only says that countable unions of countable sets are countable. If the sets aren't countable, or if the number of sets that you are unioning together is uncountable, you can't use this result. Right, so that's the main point. Okay, so by the way, my strategy for this, for how I'm going to do this proof, this is a big result. So it's not just a one-liner by any means, but my strategy is going to be to create a surjection from n cross n to this union. Remember proposition 2.12? If the domain is countable and you create a surjection onto something else, then that other thing is still countable. So I'm going to ultimately try to make a surjection from n cross n, which by the way we just proved is countable. So I'm going to take n cross n, which is countable, and make a surjection that goes on to this union. Okay, so I have to set up the notation for this a little bit. First of all, since I is countable, there exists a surjection already that would go from the natural numbers onto I. All right, so because I is countable, I know that I can do that. Let me just make sure that that this is clear to everybody. Countable just means two cases, right? The countable set I, it's either finite or it is in bijection with n, right? So this set I is either in bijection with n, which means that your onto function would work, right? A bijection is always onto. Or if I is actually finite, so let's just remember finite is one of the allowed cases of countable. If I was finite, then you're not going to make a bijection here. You're only going to be able to make a surjection. Okay, so some people out there might be wondering, why am I not assuming that f is a bijection right now? And that's because I don't know that I is countably infinite. What I know is that I is countable, which means it might be countably infinite or it might be finite. There's two possibilities. But either way, I know that I can make this surjection. Either it's a bijection or you have a finite set I and you've got all of the natural numbers that can certainly make a surjection onto a finite set. Okay, so that's why I can do that. And I'm going to do exactly the same thing with these A sub alphas now, because the A sub alphas are also finite. Okay, so similarly, since A sub alpha is countable, there exists, I'm going to call it G sub alpha, going from the natural numbers onto A sub alpha. So again, that's an onto function. Okay. So I've got all, and this is, by the way, this is for all alpha in capital I, in capital I right here. Yeah, so that's how that's going to look. Okay, so very good. So now, is everybody okay with my sort of setup here? Do I need to slow down a little bit? Just make sure. I'm going to take a drink. The air over here is so dry. When it's like 30 degrees outside, there's usually no humidity with it, so my throat struggles to get through all this lecturing, but I've got my drink here, so hopefully I'll make it. Is everybody with me here? If you have a countable set, you can make a surjection from the natural numbers onto it. It might be a bijection, but I can't guarantee that. At the best I could say is that there'll be a surjection. If I is finite, we're not going to have a bijection here. Okay. So what I'm now going to do is create what is ultimately what I want, which is to define a function. I'm going to use h for this one. And h is going to go from n cross n over to the union of these A sub alphas, where the union is running over the alphas in capital I. So I'm now going to define a function here. And how am I going to do it? Guys, this is kind of the part of the proof where I'm pulling a rabbit out of the hat. I'm kind of just creating this H out of the sky, and it's something that I had lots of time to think about before class, but I'm pulling this H out of the sky and we're going to see if it works. Okay, so how am I going to define this function H? Well, I'm going to go H of A comma B. So I'm going to input two natural numbers here. And I'm going to apply G to F of A. G sub F of A. So guys, now F of A is some index value, right? If you look back at what F is, the outputs of F are from the index set capital I. So that F of A is just one of my alphas, right? That F of A is just one of my alphas, and I'm looking now at G sub alpha of B. So I'm just going to apply that to B. So let's not get lost in this notation here. I know it's a little abstract. This subscript is just one of my alphas. It tells me that I'm talking about G sub alpha here, the alpha being F of A. That tells me which of my A sub alphas I want to consider. And then we apply this function G, which takes every natural number like B and spits out something from A sub alpha. So this output is in the union of all of the A sub alphas. You see that? Because after all, it's G of something, right? G of some natural number is always in one of my A sub alphas. And so, of course, this output lives in that union. That's exactly right. And now what I'm going to claim here, what I'm going to claim about this, my friends, is that H is onto. This is where we suffer a little bit from me only having two whiteboards to use because we've had to erase some things. But does everybody remember the recent proposition that if I create an onto function and the domain is countable, then the codomain is countable? This was proposition 2.12. We did it half hour ago or so, right? So that's exactly why I want to prove this claim. Okay, so if I can prove this claim, then I will actually be ready to finish my proof. So let's try to prove the claim. How am I going to do that? Well, I'm going to pick, to do the claim here, guys, I'm just going to call it X. X is some element of this big, huge union of A sub alphas. Right, so X lives in the union of all of those. And I have to find a preimage for it. I have to find a preimage for X. This is the idea. I have to find a preimage to show that H is onto. Well, since X is in the union of all of those A sub alphas, then that means that X lives in, let's say, A sub alpha naught for some alpha naught in the index set capital I. So this is just the definition of union. The definition of the union would tell us that. Okay, so there's this alpha naught that we've identified in capital I. Guys, remember that F, the F that we had up here originally at the top of the proof, was onto capital I. So this alpha naught, which is in capital I, has a preimage under F, right? So I'm going to use that right now. So since F is onto, there exists, what do I want to call this? I'll call this n in the natural numbers. So there's some natural number with f of n equal to alpha naught. Okay, so we can do that. Okay. Now the other thing we know, not only is f onto, but so are all of these g sub alphas, including g sub alpha naught. So anything that's in the A sub alpha naught has a preimage under G sub alpha naught. G sub alpha naught is onto. So let's use that as well to cook up another preimage. So since G sub alpha naught is onto, right? That's what it says up there, right? In our proof, there exists a G sub alpha naught, which is onto. So there exists, I'm going to call it M in the natural numbers, with G sub alpha naught of M equal to X. So this X lives in A sub alpha naught, right there. Right? X lives in A sub alpha naught, which means that there is some natural number that G sub alpha naught will map onto X. It's just using the onto property. So thus, I think we're in great shape now. What is H of n comma M? Here's the formula. Well, let's just check this out. H sub n comma n, that's just going to be G sub f of n applied to M. But f of n is alpha, so this is just, alpha naught, so this is just G sub alpha naught of M. And guess what, guys? That equals X. That does equal X. So that finishes my claim. That does prove now, if you're with me, that does prove that H is onto. All right. I'll take a breath. Is everybody good? Yeah. I hope I'm not going too fast. It's a lot of notation, actually, but there's nothing too terribly deep here. This is just, again, definition of onto. Really, you see it about 4 times on this one board. So I've written out all of these notes really carefully. I don't even think there's a single typo on this. So if you've got it written down, it's definitely worth reviewing it maybe over the weekend. This is one of the most, I'm probably going to ask you to prove this at some point. Again, this is one that's really worth learning. We're not done yet, by the way, with the proof, just to be clear, but I'm just pausing for a moment to give people a chance to breathe. Right? This is a really, really nice result. So, guys, let's just reflect for a minute. We have H right here. N cross N, that was already countable. And now we've proved that this H is onto. So that means that, do you remember the result that said if I have a function from A on to B, and if A is countable, then so is B? That's all we have to use. That's all we have to use. So thus I'm just going to say, since N cross N is countable, we proved that in the lemma, right? Then by, I think it's proposition 2.12 part 1, the union of all of these A sub alphas, where alpha is an element of I, is countable. Wow, that's it. I'm gonna put a smiley face in my proof because I really like this proof. I like the result. It's a powerful result in set theory, and I think that that's a really nice proof as well. I usually, you're asking me in the chat if we could somehow define H differently. I'm sure we could tweak this somehow, like I could switch the roles of the A and the B, for example. I might even be able to tweak the output a little bit, but I think the spirit of how this proof would be set up wouldn't change that much. You might be able to cosmetically come up with a variation of what I've done here, but the idea behind it is more or less exactly what you see right here. Okay, so yeah, this is really kind of the standard part of the course way of doing this. Okay, we're going to take a little break in a minute, but before we do that, I have to give you a couple of applications of this, and I'm too excited to wait 10 minutes. Okay, so I want to do it. So I can come back over here. I want to show you how you can use this result now to show that tons of things are countable. Let's get this erased a little bit, and then we'll write down. I think the book actually lists these as a corollary. So I'm going to write this as corollary 2.4. And it just says the following sets are countable. Okay, so the first one is one that we actually already proved, Z, the integers. But so is Q, the rational numbers. I promised you on Tuesday that I was going to do this today. And another one would be Q cross Q. So let's just look at that. Guys, if you wanted to directly create a bijection between, say, Q cross Q and N, it would be a nightmare. It would be a nightmare to go back to the definition of countable to prove that Q cross Q is countable. But in one line, I can prove it now. Okay, so I'm going to do the proof here because it's really neat to see how this works. So first of all, actually, let's just do all three of these in order. Now the integers, right? The integers, you remember from Tuesday, I did prove that one directly by creating that. You remember that function where I did something for the even values of n and then something else for the odd values of n? I kind of staggered my, okay. forget all that. We have an easy way now to prove that Z is countable. So Z is equal to the natural numbers union 0 union, I'll write this as negative natural numbers, which really just means the negative integers, okay? So this is countable, right? So countable, the natural numbers are already countable. This one is finite. Finite sets are part of what a countable set would be. And then the negative integers are obviously in bijection with the positive ones, so those are also countable. So here we're taking, guys, a union of countable sets. And it's a finite union. The number of sets is finite. And so if it's a finite union, then it is a countable union. It's a countable union of countable sets, which by our theorem must be countable. So thus, V is countable. So that's the first one. That's the first one. Let's go to Q. Oh my goodness, guys. To prove that Q is countable directly from the definition, if you said I want to list out all fractions in a manner that I could keep track of, where every fraction was in my list, I don't even know how I would do it. Actually, you probably, if I have any diehards out there, you probably could come up with a function, but I'm going to tell you right now, is not going to be fun. Okay, not going to be fun. So let me give you the 2-second proof that Q is countable, right? I can write Q. Would you agree that I could write Q as a union of sets that look like M over N, where what I'm going to do here, guys, is I'm going to let M be an integer. Now, in this notation, I'm letting my numerator be some integer, and the n here is actually some fixed natural number. So I'm going to let n go from 1 to infinity. I'm going to make this union. This just means n could be 1 or 2 or 3 or 4, right? And so on. You with me? Well, guys, when n is 1, I just get all of the integers. All right, that's countable. When n is 2, I just get all of the fractions like 1/2, 2/2, 3/2, 4/2, 5/2, 6/2. That's countable. That's just, again, the same size as the integers, right? When n is 3, I just get 1/3, 2/3, 3/3, 4/3, 5/3, 6/3. Those are all just, again, indexed in the same way as the integers are. Every one of these sets is countable because it's basically a copy of Z. I can make a bijection, right? I could actually send little m and map it to m over n. And that would be a bijection from the natural numbers, from the integers onto this set. And so this is countable. And then how many sets am I unioning together here? Well, n could be 1 or 2 or 3 or 4. That sounds like a natural number's worth of sets here, right? Like how many sets are being unioned together? There's 1 for every positive integer. That is a countable number. There are a countable number of positive integers. So this is a countable union of countable sets. Thus, Q is countable. I'm talking a lot, but I'm not writing very much. I don't have to write very much because this proof speaks for itself. It's pretty much clear that you're taking a countable union of sets that are all of size of Z, and Z was already countable. I love it. By the way, you don't even have to worry about, some of you might be wondering, what if the fractions are not in lowest terms or something? Like what if I had like 4 over 8 would be here, and then we'd also have 5 over 10. That's actually not really an issue here because we're just, if we see a repeat, so if I have 5 over 10, I can just throw it away and just say, well, I already covered it with 1 over 2. So if you're worried about the fact that there might be fractions represented in many different ways, that's a valid point. but we only need to keep sort of one lowest terms version of every fraction. And that, if nothing else, that just weeds this set down. It just cuts it down so it's not even as big as it was when you sort of looked at it from face value. So yeah, so that's actually all you have to say. So there's the integers are countable, q is countable, and finally, what about q cross q? Well, this one is just very easy as well. This is just going to be a union where P is an element of Q of the set of P comma Q such that Q is an element of the rational numbers. Okay. So in this case, I want you to imagine that you fix P for a minute. Pick your favorite fraction, maybe 3/7, right? Whatever it is. You fix that value of P and then you look at these pairs. 3/7, comma, Q. Well, that's exactly in bijection with just Q, right? The number of pairs that you would have that have a 3/7 in the first slot and any rational number in the second slot, that would be just the same set essentially as Q itself, which is already countable. So this is a countable set for each fixed P. And then how many sets am I unioning together here? Well, there's one for every rational number. And so how many is that? That is a countable number's worth, right? The Q is already countable, so this is a countable union. There's countably many rational numbers that we're unioning here, and the sets themselves are countable. So by our theorem again, thus Q cross Q is countable. I think there's a homework problem for next week that asks you to prove that if A and B are countable sets, then so is A cross B. Guys, it's literally this proof. I hope you don't spend more than like 2 minutes on that problem. It's like you just basically, instead of Q and Q, you just use A and B, right? Notice that nowhere on this board did I have to create a function. Nowhere on this board did I have to worry about whether something was one-to-one or onto or a bijection or anything. This theorem has cleaned it up for us so nicely, right? Now, these proofs are all so quick to do by just citing that theorem. Now, if somebody did challenge you and say, oh, I want to see the bijection, right? I want to see the bijection of Q cross Q with N. That's going to be that's going to be some work, right? At that point, they're basically saying, we don't want you to use the theorem. We want you to be clever and creative and come up with this bijection. That might take some extra Wheaties in the morning to be ready to tackle that kind of a question. But anyway, to just prove that these sets are countable, you can see how short everything is now. This theorem has just made everything beautiful. Ayushi has a question about, can we do the same kind of thing for intersections? Remember, when you intersect sets together, you actually make them smaller. And so if you were intersecting things that were countable to begin with, then we would just know from the earlier propositions, right, that a subset of a countable set is still countable. So we don't really need the full power of this theorem for that. This theorem is powerful because when you take a union, you're making the set much bigger. And yet still, we can somehow control it and have it still be countable as long as it was a countable union of countable sets. I love it. Oh, I'm having so much fun, and we're just getting going for the semester. Let's take a 10-minute break. I know I've been talking for a while. When we come back, we'll have just less than a half hour to go, and I'm going to talk about some uncountable sets and give you a few examples of those as well. And we should be able to finish this whole chat about cardinality in this last little bit. So at 2:25, guys, we'll rendezvous back up here again, but feel free to take a little screen break, and see you soon. Guys, if you're somewhere out there within the sound of my voice, I will probably start up here again in about another minute or so. So this is a good time to find your way back over to me. Anybody got any big plans for the weekend? Let's see. It rained over there, didn't it, recently? Finally? A little bit? Did anybody get rained on in California? I've been so worried that it's been so dry and everything. Was there finally a little bit of rain?
About 3 days ago, I think. 2 or
3
3
days ago, there was a little bit. Okay, well, at least that's something.
It didn't last very long, but it was nice while it lasted.
Okay. Yeah, free car wash. That's right. Yeah. I'm really bad about that. I'll have my car and it's like the dirtiest car in the lot. It's got dust and dirt all over it, and I'll be like, oh, but it's gonna rain, so I'm just gonna wait until the rain. Then I get a free car wash, and then it never rains, and then my car is looking really bad. Everybody knows which car is mine. Anyway. Well, I'm big into hiking, and I'm hoping that by the time I get back there, the weather will be good for that. Heading into February, we'll have to see. It's definitely a cool time of year. It's not too hot, so maybe I'll be able to get outside a little bit. Yeah, we'll see. I'm excited to be coming back.
Where do you usually hike?
Oh, I've hiked all over the San Gabriel Mountains, and probably this time of year I wouldn't go up to the Sierra Nevadas. It's a little too snowy up to do the big mountains, I guess you could call them. But I have lists of mountains that I'm trying to climb. I'll have to show you guys some pictures when I come back and get inspired for it. Yeah, I've done Pikes Peak twice, June. That's out in Colorado. So I've done more in Colorado than I have in California, that's for sure. But there's always more to do. Every time I climb one mountain, I find 2 more mountains that I want to climb. So I'm trying to make plans for the summer and figure out where I'm gonna go, but a lot of traveling. But yeah, I was worried because of all those fires. I thought, oh, they're gonna shut down a lot of the trails and everything with all the smoke and fires. But hopefully that's gonna die down. Hopefully a little more rain will come in. But anyway, enough about all of my hobbies. Let's get back to talking about another one of my big hobbies, which is math. And I want to actually show you this next theorem here, guys, that will help us understand how to show that something is uncountable. Now, again, the definition of uncountable is just that it's a set that is not countable. Countable just means there exists some bijection from the set with the natural numbers. So to prove directly that a set is uncountable, we would have to prove that there does not exist a bijection. And proving that something does not exist is always kind of a fumbling around in the dark kind of approach, right? It's like, oh, how do I prove that something doesn't exist? So turns out that the best way for a mathematician to do something like this is actually by way of contradiction. Let's assume that, in this case, the closed interval 0 to 1 is countable. Let's assume that. So I'm going to do this, guys, by way of contradiction. By way of contradiction. So suppose there exists a function f going from the natural numbers to the closed interval 0, 1, and I'm going to write the word bijection here. By way of contradiction, suppose there is a bijection between the natural numbers and the closed interval 0 to 1. I'm actually going to write out sort of what the images of this function are. Now, we don't know anything about f specifically. Like, we don't have a formula for it. We don't know exactly what it looks like, but we do know it's a bijection. That's the only thing we are allowed to assume here at the beginning. I'm going to write f of 1 and f of 2. I'm gonna make a list here of the first few outputs of this function, maybe something like this. Every one of these outputs has to be in the closed interval from 0 to 1, which means that you could write it as a decimal, right? So I could write f of 1 as a decimal, like point, and then I'm just gonna write the digits here, guys. A11, A12, A13, A14, and it might go on forever, right? You guys know that irrational numbers will have an infinite decimal representation. So this is just some output. We don't know what it is. The second one is going to be point A21, A22, A23, A24, and so on, dot, 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 right? Now, these could go on forever or they might not. They could also stop after a certain number of digits, but you could always just add a bunch of zeros at the end if you wanted to make that go forever. And then the third one is going to be point A31, A32, A33, A34, and dot, 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 like that forever. Okay, so we could imagine writing all of this out, and notice that I'll just note this down here just so you have the notation that each of these AIJs is just some digit. So it belongs to the set from 0 through 9, right? So this is for all I and j. So for every I and j, those are just digits. Those are just digits, okay? Now, we're assuming that f is a bijection, which means it should be onto. And if it's onto, that means that every single number between 0 and 1, every single real number in the closed interval 0, 1 should be equal to f of something. But you know what I'm going to do right now? I'm going to construct a number in that closed interval that is not any of these outputs. It's not actually hit by an arrow coming from f. I'm going to contradict the fact that f was supposed to be onto. F is supposed to be onto, but I'm going to come up with something in the codomain that is not going to be in this list. And how am I going to do that? So what I'm going to do is we construct a sequence of digits. By the way, we're going to talk about sequences a lot in just a couple of weeks here. But we're going to construct a sequence of digits. I'm going to call them b sub I. And what is b sub I going to be equal to? Well, here's what we're going to do. We're going to make it equal to 8. It's going to be a digit. So it's going to be equal to 8 if a sub I is not equal to 8. And it's going to be equal to 4 if a sub I does equal 8. And this is for each I in the natural numbers. So for every natural number, so B1, B2, B3, B4, right? I'm going to make a decimal digit. So what I'm going to do then, guys, is I'm going to look at the decimal point B1, B2, B3, B4, and so on, dot, 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 right? What is this, what is this number I just created down here? This number is just a big string of 4s and 8s. By the way, there's nothing special about 4 and 8. You can do this proof with any 2 digits that you want, okay? But this is definitely just a string of 4s and 8s, right? So it's point something, 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 something. Would everybody agree for sure that that is in the closed interval 0 to 1 somewhere? By the way, I should mention also, like, you might be wondering about what's the decimal representation of 1. 1 is actually, it has something to the left of the decimal point, but you can represent it as 0.999999999 forever, right? If you have an infinite string of 0.9999999 forever, that's actually equal to 1. So 1 is in this, it is expressible as a decimal in this form. But you know what, guys, this element that I just wrote down right here, it's not going to be any of these. Why not? Well, because B1 is not going to be the same digit as A11. You see that? B1 is not the same as A11. If A11 is 8, B1 is 4. If A11 is not 8, B1 is 8. So B1 and A11, they're different. And that means that this decimal digit down here isn't the same as that one. Okay? But look at the second digit. The second decimal digit is B2. Now, B2 is never the same as A22. If A22 is 8, then B2 is 4. And if A22 is not 8, then B2 is 8. And so the second digit here does not agree with the second digit here. They're different. And that means that this is different from this one. Okay, I'm trying to convince you guys that this decimal expression down here, this whatever this is not in my list. It's not in my list, right? So the point being, let me just say, since BI does not equal AII, this number, and this is for all I, by the way. For all I, the BI and the AII are not the same, then point B1, B2, B3, this number I just created, is not in the image of F. It is not F of any natural number. It's not F of 1, it's not F of 2, it's not F of 3, it's none of these things up here. So F is not onto. Can everybody read that? Make sure that's totally readable. F is not onto, and so that is a contradiction. Okay, so we have finished our proof by contradiction here. That is a contradiction. So this is a pretty famous proof, actually, this strategy of doing a proof. You are creating a new number whose digits along the main diagonal don't agree with anything from the list that you had in this little diagonal of this little grid here. That's what's kind of neat about this. There is a name for this. I just want to, let me put a little asterisk here, guys, and I'll just explain I'll just put it over here what I'm talking about. There's a name for this. I just want you to be familiar with it. This is called Cantor's diagonalization, or diagonalization argument. So there's a name for this proof technique, and this is not the only place in math where you would see this kind of a trick, where you kind of pinpoint the main diagonal of a table of values and use that as the sort of the crux of how the argument works. But we're using this Cantor's diagonalization argument to do this proof then. Okay, it's a pretty standard technique for showing that something is uncountable. You just proceed by way of contradiction. Assume that it is countable, and then imagine that you have this bijection, but then wait a minute, your bijection somehow is not onto. It fails to have every possible output coming out of that function that you're supposed to have. So yeah, it's a nice argument. Once we know that we have an uncountable set, though, then any superset of it is also uncountable. Remember our propositions from earlier today? And anything that's in bijection with 0, 1 is uncountable. I think one of your homework problems for tomorrow is to prove that the interval 0, 1 is in bijection with AB. Something like that. Well, if you know that this one's uncountable, then that one's also uncountable. By the way, I've drawn this as an open interval. The theorem here states it as a closed interval. Maybe I should add a few more notes here about this. So I'm going to actually add another corollary, and then I'll come back to that open versus closed interval point. So another little corollary here, guys, is that the real numbers and the irrational numbers. So I'm going to look at the set difference again. So take the real numbers and remove the rationals from it. These sets are both uncountable. These sets are both uncountable. So I'm going to do the proof here. These are easy to prove. So the real numbers are uncountable, and so are the irrational numbers, the ones that are not rational. So for the proof, since the closed interval 0, 1 is a subset of R, then R is uncountable, right? And that'll be by theorem 2.5. We just proved that the closed interval 0, 1 is uncountable, together with that proposition. So I'll put it here. It was proposition 2.11, part 4. So part 4 of Prop 211, which we did earlier in the class today. So that proves that the real numbers are uncountable. Okay. How about for the irrational numbers? I am going to do that by way of contradiction as well. By way of contradiction, if R minus Q, so if we do the set difference, so we just remove the rational numbers from the real one, so that should say if R minus Q was countable, does anybody have an idea how I'm going to do it from there? If the irrationals were countable, how would I get a contradiction here? If you have any ideas, you can throw them in the chat or you can use your microphone. I don't care which. Can we take the union of the irrational numbers with something else? Does anybody know another set that is countable, that's kind of related to this? Yeah, the rational numbers, we proved that using that big theorem 2.4, right? The countable union of countable sets is countable. The rational numbers are countable. And if these were also countable, so if the rationals are countable and the irrationals are countable, that would be proving that all real numbers are countable, which we just proved is not true. Okay, so then R would be Q union R minus Q. Right? If you think about it, every real number is either rational or irrational. And if the R minus Q was countable, we already know that Q is countable. We would then be having, this would just be a countable union of countable sets, which would have to be countable. We would then say that R is countable, but it's not. We just proved that R is uncountable. Okay, so let's write that down, which is a union of two countable sets, thus proving by, I'll put this in parentheses just so you have it for your notes, taking a look at that big theorem again, theorem 2.4, thus proving that R is countable. And that is, of course, a contradiction. That's a contradiction. Okay. Does everybody understand that argument? If you do, then I want to do one more example and I want you guys to help me with it. I want to do one more example, which is the open interval 0, 1 is uncountable. So I want to prove this one. Okay. Now remember, we already proved that the closed interval is uncountable. Now, when I remove the endpoints from that closed interval, the set does become smaller. And in general, when you take an uncountable set and you make it smaller, it could become countable. So I can't just, immediately take this subset here of the closed interval 0, 1 and say, well, it's got to be uncountable. So how could I make this proof work? I know we've been doing this for almost 2 hours now, but honestly, this one is a slam dunk if you followed what I just did a moment ago. Which proof technique should I use?
Contradiction.
Yeah, I like it. Let's do contradiction. Let's suppose it's countable, right? So for the proof, if the open interval 0, 1 is countable, then so is any finite union consisting of countable sets. And what we could recognize here, guys, is that the closed interval 0, 1 is literally I'm basically doing the same idea that I did over here, right? I'm just going to take the open interval 0, 1 and I'm going to union that with its two endpoints, right? So I'm going to take the open interval 0, 1, which is by assumption countable. The individual sets of 0 and 1 are finite. There's only one element here and there's one element here. Finite things are always countable. So this is a union now of 3 countable sets, therefore countable. And so that would be a contradiction. We know that this one is not countable. So I'll just say which is a union of 3 countable sets. Remember, a finite set counts as being countable. So these are 3 countable sets. You're taking the union of 3 countable sets, hence countable, which contradicts that, which is by theorem 2.4. Sorry, hence countable. This is by theorem 2.4. Contrary to, I guess I've erased it now, but theorem 2.5 basically said that theorem 2.5 basically said that the closed interval 0, 1 is uncountable. So if the closed interval 0, 1 is uncountable, then we have a contradiction because it looks like we just said that the closed interval 0, 1 was countable. Make sense? Nice. So the open interval 0, 1 is uncountable, and so as another quick follow-up, then any interval, doesn't have to be 0 to 1, any interval AB is uncountable. And the proof for that is actually going to be coming from your homework assignment. So I'll just say homework number 2 that you're doing actually for tomorrow night. One of your problems is to prove that the interval 0, 1 twiddles the interval AB for any A and B. Right? So again, as soon as 0, 1 is uncountable, then anything that twiddles it is still also uncountable by those earlier propositions today. So that would pretty much wrap that up. Questions here about any of these? Guys, we've come to the end of, this has been a big section. We've used most of this week on the conversation about cardinality, but I like doing this because it's also a good review of functions, specifically talking about one-to-one and onto functions and how to create these things and check these things. So I like to do this in the first couple of weeks of the semester. Where we need to go to next, just to give you a heads up, is we are going to jump back to the start of chapter 2. When I come back to Fullerton next week, we're going to start right at the top of chapter 2. I probably won't even do a recap of this because this is really putting a period on it. We're going to go into something totally new, and we're going to start talking about the construction of the real numbers. So there are axioms that we have to have. Some of them are algebra oriented axioms, like how does addition work and things like that. Things like associative, distributive, commutative rules. But then also the notion of one number being bigger than another. So this inequality idea, which is really very important in real analysis, we're going to list out those axioms. These are assumptions we're going to make about how the real numbers work. And then from there, chapter 2 is mostly about sort of just the structure of the real number set. We're not going to get into the actual calculus stuff until later. We have to, ultimately we'll talk about limits, but we're not quite there yet. We need to spend a little time just really appreciating kind of how the real numbers work. We've already seen one kind of quirky thing, which is that the rational numbers, which seems to be everywhere on the real number line, is much smaller than the entire real numbers, right? One of them is countable, the other one is uncountable. So there's a few other quirky things that go different between these different subsets of the real numbers. And even just comparing open intervals to closed intervals, people who are interested in something called topology would spend a lot of time like really investing into this. So next week, we will spend some time doing a little bit of that in chapter 2. I'm super stoked to be coming back to get to meet all of you in person next week. For the rest of this week, tonight's office hours and tomorrow's office hours, remember, I'm still just Zoom only. But I hope this has worked out okay, reasonably for 2 weeks to kind of just use my parents' basement. They've really appreciated having me here, but I think they're going to be just fine. And I'm going to come back and see you guys next week. How does that sound? Awesome. All right. I'm looking forward to that. For now, I'm going to let you go. We're all done for today. And I will see you in office hours in the next couple of days, or else by next Tuesday at the latest in person. I hope you have a great rest of your day. Stay safe out there, and I will see you all again soon. Bye for now.
Professor, for the purposes of this class, we're using the book's definition of the natural numbers that 0 is not contained in N.
That is true. Usually it's just the computer scientists that want to put 0 into the natural numbers. We are excluding 0 from the natural numbers, just so we can all be kind of in agreement and on the same page. Yeah.
Okay. And tilde
Good point.
tilde means bijection.
Yeah, that's right. That's just the abbreviation. The book uses it too. So yeah, you got it.
Got nothing to do with the number of elements in the set. It's just bijection only.
Yeah. Good way to think about that. Absolutely.
Oh, yeah. Thank you.
Awesome. You're welcome.